Now, let's try to understand some of the applications of derivatives. And one of that major application of derivatives is this maxima and minima. Finding out the maximum value of a function and the minimum value of a function. Generally, when you look at any function, it could follow some such kind of a shape like this. There will be some maximum value, some minimum value. It could follow some kind of a shape. It could be a straight line or it could be some kind of a curve. So let's assume if this is the kind of a shape of a particular function that we are looking at. So it is taking some kinds of ups and downs for different values of x. For if the x is this much, the value of the y or the function is a negative value. Whereas if the value of x is this, we see that the value of the function is a positive value here. So somewhere else, if I'm looking at this, I'm seeing that the value of the function is something here. So all we could see is different possible maximum values and different possible minimum values are coming up. Now, how do I really use the concept of differentiation to identify what are these maximum points and what are these minimum points? For that, what is maxima? Wherever you are looking at a maximum value, it is looking like a hump, wherein value before the hump is like a decreasing, which means there is an increase from here up to the hump, and after that there is a decrease. That is where the maximum will occur. So which means at this maximum point the derivative is 0, and wherever the derivative is 0 we call them as the critical points. And after the maximum point we see that the graph will start moving downwards. And the same fundamentals are applied even to your minimum. In the case of the maximum, the graph looks like a hump, whereas in case of a minimum, the graph looks like a valley, right? You see kind of a valley like this. So from a certain point, there is a decrease, reaches a minimum, and after that, there is an increase. Again, applying the concept of derivatives, at the minimum most point, the derivative will be 0. And that's the reason it also becomes a critical point. And so whenever we are saying the derivative is 0, at this particular point, the function will neither increase nor decrease. So how do I use the concept of derivatives to find the maximum or the minimum value of a function? The first step, find the derivative of the function. And once you find the derivative, equate it to 0. We'll take the example in the next slide. But first find the derivative of the function and equate it to 0. So once you have equated it, you will be able to solve the critical points. You will get 1, 2, 3, any number of critical points depending on the equation. And based on that first derivative, you take the derivative of that again and substitute all the critical points that you have got in the previous example. And wherever that second derivative after the substitution of the critical point turns out to be positive, you say that at that particular point the value is minimum. And if the second derivative turns out to be negative, you say that that particular function is having a maximum at that particular point. That's a straightforward way of solving for maxima and minima. Let's look at a couple of examples. Find all the local maxima and minima of the function k of x is x cubed minus 3x squared minus 24x plus 5. So what do I do? the first step, find the derivative of this. So the derivative of this is 3x squared minus, what is the derivative of 3x squared? It is 6x minus 24. So I am finding the derivative of this, equating it to 0. So when I have equated it to 0 and simplifying it, this becomes x squared minus 2x minus 8 equal to 0. So if I solve for x, I'll write it as x minus 4 into x plus 2 is equal to 0, making it x equal to 4 or minus 2. So this 4 and minus 2 are my critical points. X equal to 4, x equal to minus 2 are my critical points, which means my second step is also done. Now I have to find the second derivative. So what is the second derivative of this? 2x minus 2. So the second derivative is 2x minus 2. Now substitute both the critical points. If I substitute 4 in this, 2 into 4, 8 minus 2, making it 6. Whereas if I am substituting x equal to minus 2, minus 4 minus 2, it is minus 6. So when I am substituting x equal to 4, I get 6. When I substitute x equal to minus 2, I get minus 6. So because I got the second derivative value as positive, I say that this is, at this particular point, the function is having a minimum value. And the second derivative I got negative here. So at this particular point, the function is having a maximum value. And now if I have to find what is the minimum value, substitute x equal to 4 in the original function. So if I substitute x equal to 4, 4 cubed, 64, minus 3 into 4 squared, 48, minus 24 times 4, 96, plus 5. So this is the number which is the minimum value, minimum most value that is possible for this function. 16 minus 96 minus 80 plus 5. Minus 75 is the minimum value for this particular function. Whereas if I substitute x equal to minus 2, it becomes minus 8 minus 3 times minus 2 squared minus 12 minus 24 times minus 2 is plus 48 plus 5. So I get a value of 53 minus 20. 33 is the maximum value for this function and minus 75 is the minimum value for this function. So this is how we build the maxima and minima based numerical question. All right. Let's take one more example quickly. The second one, find the local maxima and minima of the function x plus sine x. What is the first derivative? First, I'll take the first derivative. Derivative of x is 1. And cos sine x, the derivative is cos x. Equate it to 0. So it is coming out like cos x equal to minus 1. When is cos x minus 1? Cos 2 pi, or when you say cos pi, which is 180 degrees. For cos 180 degrees, it is minus 1. So which means x is equivalent to pi. Right? X is equal to pi is what I have solved it. Then you go for the second derivative. 1 plus cos x. What is the second derivative? Minus sin x. And I'll substitute x equal to, only one value I got, so I'll substitute x equal to pi. Minus sin pi. When I am substituting minus sin pi is 0. So it is coming out as 0. When it is coming out as 0, I am not getting any kind of a maximum or a minimum. Only if I have a negative value or a positive value, that is when I talk about a maxima or a minimum value. So in this case, no such thing exists. Let's take another example, the last one. The sum of two positive numbers is 60. X plus y is equal to 60. How can we choose them so as to maximize their product? Okay, I want to maximize their product. So I'll say one of them is x, the other one is 60 minus x. Right? I want to maximize their product, which means I have to maximize this function x times 60 minus x, which is nothing but 60x minus x squared. This is the function that I have to maximize. So I'll find the first derivative. What is the first derivative? 60 minus 2x. Equate it to 0. 2x is 60. X equal to 30. Now find the second derivative of this function. F double dash x. What is the second derivative? Minus 2. Minus 2, I don't need to substitute any value because it's a constant. Minus 2 is a negative value. And because it's a negative value, the second derivative is negative, which means at that particular point, I can say that there is a maximum value for this function, which means the function is having a maximum value at x equal to 30. So the two positive numbers are 30 and 30. If I select them, that is when the product is maximum. So 30 into 30 is 900. I can't create any product that is more than 900 by using two numbers which sum up to 60. So that is the kind of an application. All right, let's look at some quick real world examples as well. A box is to be made from a sheet of cardboard that measures 12 by 12. Okay, I'm creating a box from a cardboard. The construction will be achieved by cutting a square from each of the corners of the sheet. Okay, so I'm cutting a small square from each of the corner of this sheet. Correct? And folding up the sides. What is the box of the greatest volume that can be constructed in this fashion? Now I'm folding it in such a way that the length, so initially it was 12. So because I'm cutting two sides from each side, this will become 12 minus 2x. And even this side will become 12 minus 2x under the assumption that I am cutting x part from each side. I'm cutting x part from each side. So the length of the box will become 12 minus 2x. The width of the box will become 12 minus 2x. And the height of the box will be x. Because that x is folded upwards. So what is the volume of this particular box? Length into breadth into height. So the volume of this particular box is x into 12 minus 2x into 12 minus 2x. So as good as x times, if I go and substitute it, 144 plus 4x squared minus how much? 24x minus 24x minus 48x. So the simplification is coming that the volume is 144x plus 4x cubed minus 48x squared. So this value I have to maximize. So which means after this again it's an application of the maxima minima. Find the derivative. 144 plus 12x squared minus 96x. So make it equal to 0. I can cut out 12 across. So which becomes 12 plus x squared minus 8x equal to 0. X minus 6 into x minus 2. So x is either 2 or 6. There are two different points coming out. So x could be either 2 or 6. Now let's look at what is the second derivative, because I want to know at which point the maximum occurs. Is it at 2 or is it at 6? Because I got two possibilities here when I did the first derivative equating to 0. So I really need to know where is the maximum coming. If I cut 2 from each side or 6 from each side, that is where I go with the second derivative. The second derivative here is 24x minus 96. Substitute x equal to 2. When I substitute x equal to 2, 48 minus 96 is minus 48, negative negative value, which means there is a maximum. Good. Now substitute x equal to 6. 24 6 is 144 minus 96, which is 48. At 48, I'm going to get, it's a positive value, which means at x equal to 6, I'll have a minimum value. So at x equal to 2, I'm going to get a maximum value. So which means I cut 2 from each side. So this side I cut 2, this side I cut 2, which means 8 is the box on each of the sides and 4 is the height. That is when I get the volume to be maximum. And what is that maximum volume I can get? I can substitute 2 here. 144 into 2, 288 plus 4 times 2 cube. 2 cube is 8, 8 4 is 32. Minus 48 times 2 squared. 48 times 4, how much? 192. 288 plus 32. 320 minus 192, almost 208. So this much of volume is what is created by this particular box. That's the maximum volume I can create by using this kind of a sheet, creating it into a box like this, right? So that is where we are applying the fundamentals of maxima and minima. Probably a couple of other numericals are just given to you. If you want, you can do the practice in a similar manner. But the basic concept or fundamental behind the maxima and minima really has a lot of applications in the real world, which generally uses the concepts from the derivatives world. All right. Now, let's try to understand another important aspect in the derivatives. Till now, whatever the applications that we have looked at are the functions of only one variable. Like in the earlier examples that I have taken only one variable at a time, differentiated it, equated it to 0. So I have done only for one variable. But if my function has more than one variable, something like this, I am having a function f of xy, which is 2x squared minus 3x squared y plus 5y plus 1. So something in x and something in y. And if at all I want to find the derivatives, so this is where I'm talking about find the derivative with respect to x by holding y as constant, right? I'm trying to find the derivative or differentiate the function with respect to x by holding y as constant, or I am differentiating the function with respect to y holding x as constant. So if I am differentiating a function f with respect to x, I call it as dou f by dou x. In this case, y will be constant. And if I am differentiating the function with respect to y, I call it as dou f by dou y. It's not d. When it is a single variable case, we called it as df by dx. But in partial derivative, where I am keeping one of them constant and then finding the derivative with respect to the other, then I'm representing it as dou f. So dou f by dou z, dou x is nothing but it's as good as a regular derivative, right? In df by dx, if you want to remember the usage of limits, I would say limit h tends to 0, f of x plus h minus f of x divided by h. This is what we were calling the derivative. Now the only difference is this function, everything is same. This function will have a y element also in it. Otherwise, everything else is the same. So these are called as the partial derivatives because the function actually contains both x and y, but I'm finding the derivative only with respect to x. So there I'm keeping y as constant and vice versa. That's the reason we call them as partial derivatives. all the rules regarding the derivatives which we have applied, they are applied even to the partial derivatives also. Whichever the formulas relating to the derivatives of different functions, I can apply them to the partial derivatives also in the same manner. And the similar kind of interpretations can very well be made even if there are 3 or more independent variables also. I just don't need 2. I could have a function in x, y, z. Everything is the same. I keep all others as constant and I do the derivative only with one of them. That is what goes as a part of the partial derivatives. So let's look at a few simple examples to work with. So if I'm saying f of xy is this much, how do I find dou z by dou x? Dou z by dou x is by I'm finding the derivative of this function with respect to x, keeping y as constant. So wherever y is there, I'll keep it as a constant. Okay, derivative of 2x squared, which is 4x, minus 3x squared y. 3y is a constant. So the derivative of x squared is 2x. So basically I'll get it as 6y, 6xy. Because 3y is a constant times 2x plus 5y. Y is a constant. So the derivative of this constant is 0. The derivative of this constant is 0. So basically I'm going to get 4x minus 6xy. So f dash, either I write it as f dash xy, or sometimes better than this representation we write it as fx of xy. Means I'm differentiating this function with respect to x. So this comes out as 4x minus 6xy. And the second question is asking find it at 2 comma 3. So which means substitute x equal to 2 and y equal to 3. X equal to 2 makes it 8. So 6 into 2, 12 times 3, 36, making it minus 28. So this will come out as minus 28, and for this I know the value. The same logic. It looks like everything the same kind of a differentiation, right? So if I'm saying z equal to e to the power of x squared plus y squared. Okay, dou z by dou x. So I have to differentiate this entire thing with respect to x. So basically, this is like a compound kind of a function. So I'll assume this entire thing to be some x. So e to the power of x will become e to the power of x itself. And to this, I'm going to find the derivative of x squared plus y squared. And here y squared is a constant. Only x squared will work. So I'll take it as 2x. So this would be the dou z by dou x. And similarly, I require f by 2 comma 1, which means first of all I need to find dou z by dou y, which is f by of x comma y. So how do I, again I'll find the derivative, which is e to the power of x squared plus y squared, and the derivative of x squared plus y squared. Now x squared is a constant, so it will be 2y. And I'll substitute x equal to 2 and y equal to 1. So it becomes e to the power of 2 squared is 4 plus 1 squared is 1. So making it e to the power of 5 and 2 times 1. So it becomes 2 e to the power of 5. That's how we simplify the numericals using the partial derivatives. Right? Let's look at one more real world example of partial derivatives. Okay, this is from the economics world. The productivity of a major computer manufacturer given by the Cobb-Douglas production function. So this is the function that we are looking at, right? X and Y. X is units of labor, Y is units of capital. So for a company, this is what is the production function, 15 times x to the power of 0.4 and y to the power of 0.6. The partial derivative represents the rate of change of productivity with respect to labor. So what is the partial derivative in this case with respect to x? So I'll take it as, so 15 times 15 is a constant. And if I'm doing it with respect to x, even y is constant. So I'll take it as 15 times y to the power of 0.6, and I have to find the derivative of x to the power of 0.4. So it becomes 0.4 times x to the power of minus 0.6. That's the derivative. So which will make 15 times 0.4 is 6. 6x to the power of minus 0.6 and y to the power of 0.6. This is the derivative with respect to x, and which is what we call as marginal productivity of labor. The partial derivative fy represents the rate of change of productivity with respect to the capital. So I say fy of x comma y. So if I find it, then x is a constant. So 15x to the power of 0.4 will be as it is. The derivative of y to the power of 6 is nothing but 0.6 y to the power of minus 0.4. So which is 9x to the power of 4 y to the power of minus 0.4. This is the marginal productivity of capital. Generally we represent it as K. If the company is currently utilizing 4,000 units of labor and 2,500 units of capital. So I know now X is 4,000 and Y is 2,500. Find the marginal productivity of labor and the capital. Okay, so how do I find the marginal productivity of the labor and capital? So let me open a spreadsheet for that. Right, let me look at a spreadsheet here. 6 times x to the power of minus 0.6. So marginal productivity of labor is nothing but 6 times x is 4,000. 4,000 to the power of minus 0.6 and y to the power of 0.6. Y is the capital 2,500 to the power of 0.6. So marginal productivity of labor has come to 4.52. Probably I make it as a number coming out to 4.53, and marginal productivity of capital works out to 9 times x to the power of zero point 0.4 into y to the power of minus 0.4. 9 times x to the power of 0.4 y to the power of minus 0.4. Y to the power of minus 0.4. So this is around 10.86. So I could see that the marginal productivity of the capital is much higher compared to the marginal productivity of the labor. Marginal productivity of the labor is 4.53, whereas the marginal productivity of capital is 10.86. For the greatest increase in the productivity, should the management of the company encourage increased use of labor or increased use of capital? What we are clearly finding is the company needs to use increased use of capital, because 1 unit of increase in the capital is increasing the productivity by 10.86 units, whereas 1 extra unit of labor is increasing the productivity just by around 4.53 units. So that's the way we can use the concept of partial derivatives to really provide a real world solution to the problem. Right? In till now, whatever the partial derivative that we have looked at is again the first order. I just found out dou f by dou x or dou f by dou y. But in some cases, I may be required to find the second derivative itself, derivative of a derivative. Derivative of a derivative is something that I may have to find out, and that is what we are calling as the second order partial derivative. Let's, for a simple example, let's say if I am saying f of xy is x power 4 y power 7. What is dou f by dou x? I'll treat y as constant. So 4x cube. I'm taking the derivative of x, 4x cube y power 7. And if I take dou f by dou y, I keep x as constant. So I'll take the derivative of y power 7, which is 7 y power 6 x power 4. This is dou f by dou x. This is dou f by dou y. Now, again, this function, I can find the derivative of this with respect to x or even with respect to y. So I may take dou f by dou x of this particular function, dou f by dou x. So I'm again taking y as constant, 4y to the power of 7, and x cube will become 3x squared. So this will become 12x squared. Similarly, I could have found out dou by dou y of dou f by dou x. Whatever I got this, now I differentiate it with respect to y. So 4x cube is a constant. 4x cube and 7y power 6, making it 28x cube y to the power of 6. Similarly, this I can do two things. Dou by dou x I can do for dou f by dou y. So I find the derivative of it with respect to x means y is a constant. So 7y power 6 is a constant, and this will become 4x cube. So it becomes 28x cube y to the power of 6. Let me tell you here, this is just accidental that these two values are the same. In reality, need not be the case. Right? I'm telling you, when we look at a couple of other numericals, we may find that. So, or I may do dou my dou y, dou f by dou y. So, I am trying to differentiate this with respect to y, which means x is a constant. So, it is 7x to the power of 4 and 6y to the power of 5. So it becomes 42 x to the power of 4 y to the power of 5. So now this is what we typically call as dou square f by dou x squared. And this one we call it as dou square f by dou y dou x. First we are finding the derivative with respect to x and then with respect to y. This is called as dou squared f by dou x dou y, first with y and then with x. And this is called as dou squared f by dou y squared. Both the times we are finding the derivative with respect to y. And another notation wise, this is called as fxx. This is called as fxy, the second one. Fxy is nothing but first I am finding the derivative with respect to x and then with respect to y. When I say fyx, first I am finding the derivative with respect to y and then with respect to x. And fyy is the last one. So notations wise, some kind of a comfort level needs to be there with respect to the notation. Let's look at the numerical. So we have f of xy, 3x squared, 2xy cube plus 1. So I need to find out all these things. Dou squared z by dou x dou y. So which means first thing I have to find out. So it's as good as dou by dou x of dou z by dou y. So first find out the derivative with respect to y. So x is a constant. So this is a constant. I don't need to bother. This is a constant. So here it becomes minus 2x and the derivative of y is 3y squared. So it becomes minus 6x y squared. And this I have to differentiate it with respect to x. So y is a constant. So this is becoming minus 6y squared. Minus 6y squared will be dou squared xz by dou x dou y. And in some cases, he is also asking me dou squared z by dou y dou x. So yeah, this is where we'll see the difference. First, I differentiate with respect to x, and then I differentiate with respect to y. So dou by dou y of what is dou z by dou x here? So y is constant. So x is not. So which means the derivative of this is 6x minus 2y cube. So 6x minus 2y cube is the number here. and you have to differentiate it now with respect to y. X is constant, and this is becoming minus 6y squared. Oh, here also we are getting a scenario where this is the same. Okay. I'm also supposed to find now there is a question f y x 2 comma 1. F y x is first I find the derivative with respect to y and then with respect to x, which is nothing but dou x dou y, which is coming out to minus 6y squared. Minus 6y squared. So obviously if I substitute y equal to 1, it is coming out to minus 6. So even this numerical is solved. And I am simply to find out dou squared z by dou x squared, which is nothing but dou by dou x of dou z by dou x. So I differentiate first with respect to x. If I differentiate this function with respect to x, it is 6x minus 2y cube. Now I differentiate it with respect to x again, which I'll get it as 6, and this is a constant. So 6 will be my value for dou squared z by dou x squared. So it's a simple matter of solving by assuming one of them or many of them. The process goes in the same way. So assuming only one of them is variable and remaining all of them are constant. That's the way we solve the partial derivative functions. All right. Now we will move on to another important application associated with the derivatives or the differentiation, wherein we want to find the maxima or minima of a function only. We want to maximize or minimize a particular function, but subjecting it to some kind of constraints. This is what we call as an optimization problem, or typically we get them under the category of operational research kind of area, where we also call them as linear programming kind of problems, right? Typically solved through what is called as simplex method, or we also have tools like Excel which can solve them using a tool called solver within them. Now, if I have to go with that process theoretically, so whenever I want to find the maximum value of something or a minimum value of something, subjecting it to some set of constraints, that is that kind of finding out maximum or the minimum value can be accomplished through this concept of Lagrange multipliers. So I am trying to find out the maximum or the minimum value of z, subjecting it to a constraint g of x comma y equal to 0. When, if I have to do that, the simple thing is introduce one value called lambda. So make it as a function of x, y, and lambda. How do you form this? Take your f of xy as it is, which is your original, and take lambda times your constraint, and that you call it as f of xy, right? And after that, for that particular function, find your partial derivatives with respect to x, with respect to y, and with respect to lambda. So you'll get three different partial derivatives, and each one of them you equate it to 0 and solve for the values of x, y, and lambda. And that is where you can get your maximum or minimum value. The same logic can be extended even if there are many independent variables also. So if there are three also, make it in such a way that all the constraints you are separating by lambdas, lambda 1, lambda 2, lambda 3, and you differentiate, you take a partial derivative of that function with respect to each of your original variables, as well as with respect to the lambdas that you have introduced and solve them for 0. You have to compute your partial derivatives and equate them to 0 and solve for the values of x and y, x, y, z, whatever it is. And that is the kind of a function that is your maximizing function. When I take a numerical example that simplifies your entire understanding, let's look at this. Right? Okay. So what is that you have to do as a part of the steps? Write the problem in the form of the maximize or minimize something. So let's take parallelly the example also. I want to minimize f of xy is x squared plus y squared. So z is f of xy, which is x squared plus y squared. And I'm subjecting it to a g of xy, which is x plus y equal to 10, means x plus y minus 10 equal to 0. So my f of x comma y is x squared plus y squared. G of x comma y is x plus y minus 10 equal to 0. So I have written the problem in this form. Fair enough. Form the function. Now I have to form the function capital F of x comma y comma lambda. So it is f of xy, which is x squared plus y squared, plus lambda times g of xy, x plus y minus 10. This is my f of xy lambda. Then I take the derivative of x, this function with respect to x. So what is it? This is 2x. All others are constant. So this is constant. Here plus lambda x. So the derivative is lambda. Lambda y constant, 10y constant. So I am equating it to 0. So which is coming out like 2x plus lambda equal to 0, which means x is minus lambda by 2. Okay. Now the same f x y lambda, I take the derivative with respect to y. 2y plus lambda. That is what it is. Even this I am equating it to 0, means y equal to minus lambda by 2. Now I will find the derivative of this function with respect to lambda itself. So these two are constant. So if I am taking with respect to lambda, which is nothing but x plus y minus 10. So this I am equating it to 0, making it x plus y equal to 10. Now x I know minus lambda by 2, y also I know minus lambda by 2. So minus lambda by 2, minus lambda by 2, minus lambda equal to 10, lambda equal to minus 10. So I am getting lambda equal to minus 10. Right? So I'm getting a lambda equal to, subject to x plus y equal to 10, I'm getting lambda equal to minus 10. So I, from here I can get x equal to minus lambda by 2, minus of minus 10 by 2. So 10 by 2, which is 5. So from here I am getting x equal to 5 and y equal to 5. Right? So if I have to maximize x squared plus y squared, subjecting it to x plus y equal to 10, the maximum value I am getting is when x equal to 5 and y equal to 5, wherein I can put 25 plus 25 is, that's the minimum value. The minimum value that I am getting is 25 plus 25, which is 50. Right? So that is how I am getting the derivatives kind of stuff. Similarly, look at the other example. A rectangular box with an open top and one partition to be constructed from 162 square inches cardboard. Okay, the cardboard is having 162 square inches and I have to construct a rectangular box with an open top and one partition. So it needs to have something like this. So there is an open top. So basically there is a bottom, 4 sides, and a partition in the middle. Find the dimension that results in a box with the largest possible volume. So I'll take the length to be some x, breadth to be some y, and height to be some z. Okay. So if I'm talking about the total area is 162 square inches. But what is the total area of the cardboard that I require? I need one base. So which will be length into breadth, which is xy. I need two bases on the lengthwise, two walls on the lengthwise, two walls on the lengthwise, or probably three walls because there is one partition as well. So I require 3 times x times z. I require two walls on the breadth side, which is nothing but 2 times y times z. So this is the total dimension, which is 162, right? So I require xy plus, because it's an open top, I don't need 2 times xy material. Xy plus 3xz plus 2yz, I have it as 162. So let me rewrite this. Xy plus 3xz plus 2yz is 162. So I need to find the volume now. What is the volume? XYZ is the volume, right? XYZ is the volume. So I have to maximize this volume subjected to this. So I'm creating a function f of x comma y comma z comma lambda, which is xyz plus lambda times xy plus 3xz plus 2yz minus 162. So I'll differentiate it with respect to x. So which will give me yz. Then what else are there? Plus y lambda. This is my differentiation with respect to x, which I'll equate it to 0. I differentiate it with respect to y. I get it as xz plus, okay, here I have one more x, I suppose. So here it is y lambda plus 3z lambda is equal to 0. So if I'm differentiating with respect to y, I get it as xz plus x lambda plus 2z lambda is equal to 0. I differentiate it with respect to z, I get xy plus 3x lambda plus 2y lambda is equal to 0. And I differentiate it with respect to lambda, I get xy plus 3xz plus 2yz minus 1 is equal to 162. So these are my four different expressions that I am getting. Yz plus y lambda plus 3z lambda equal to 0. So I have to solve these four expressions. Right? So if I solve these four expressions, yz plus y lambda plus 3z lambda equal to 0 and all these things, that is when I'm getting my values of x, y, z, or I'll get my value of lambda there, and that is what will simplify my process. Right? X, y, 3x, z and 2yz. Okay, let's try. Xy is nothing but minus 3x lambda minus 2y lambda plus 3xz 3 times minus x lambda minus 2y lambda plus 2yz 2 times minus y lambda minus 3z lambda is equal to 0. So we are converting it into one form. So at least minus 3x, this is what, xy plus 3x lambda, this one. So minus 3x lambda, you have 3x lambda plus 2y lambda minus 2y lambda, this one also, right? So there is a lambda that is common. So I'll call minus lambda times 3x. So I'm taking minus lambda out completely. So this is 3x and this is also 3x, making it 6x. And this is equal to 162. So I have 6x minus 2y lambda minus 2y lambda minus 2y lambda. So again there is plus 6y. If I am differentiating with respect to x, it is so 3 times minus x lambda minus 2z lambda, sorry. So this is becoming minus 2y lambda minus 2y lambda. So it is 4y. And what about the z? Here I am getting minus 6z lambda and here also I am getting minus 6z lambda plus 12z is equal to 162. Now I have to solve them. No go. Right? Yz plus y lambda. So probably here I may have to substitute for one of them in terms of other and simplify the process getting the values of x, y, z and lambda. So once I get my values of x, y, z and lambda, that is what will come out as the maximum value that could be fitted with respect to this rectangular box. So the numericals have to be solved in this particular manner, but the conceptual wise, we need to have a clarity in terms of where do we typically use the Lagrangian multipliers as a part of the differentiation usage. All right. So these are the three topics as a part of the applications of the derivatives that I am covering as a part of this session. Thanks a lot for listening to this session. Thank you very much.